Hello and welcome to our lesson on section 7.3 for our trigonometry class. We're going to be going over how to solve trigonometric equations in this section. So to get started, we're going to start with a fairly easy example. We've got 2 sine theta plus 3 equals 2. And here our goal is to solve for theta. It does specify that we're looking for angles that are solutions on the interval from 0 to 2 pi. So this is our restriction. And so the first thing we need to do to solve for theta is we need to isolate the trig function. So we're going to start by moving the plus 3 to the other side. And that's going to give us 2 minus 3, which is negative 1. And then the next step is we got to get rid of the coefficient of the trig function. So we're going to divide both sides by 2. And at this point, we now have sine theta equals negative half. So if we're looking for solutions on the interval from 0 to 2 pi, what we need to do now is go to the unit circle and find all of the angles theta that have an ordered pair with a y-coordinate of negative half. Okay? So y-coordinate of negative half, that's going to be at 7 pi over 6 and 11 pi over 6. 7 pi over 6 and 11 pi over 6. And those are the only two angles within the given restriction that produce a solution to this equation. Now, what I'd like to do is show you how to check that with DESMOS. Okay? So what we're going to do on DESMOS is we're going to put in the left-hand side of the equation for one equation, and then the right-hand side for another equation. So here we have the left-hand side, y equals 2 sine x plus 3. Here's the right-hand side, y equals 2. And then we're looking for where the two graphs intersect from 0 to 2 pi. And you're going to see that there are only 2 points of intersection between 0 and 2 pi, and that is at 7 pi over 6 and 11 pi over 6, which verifies the solutions we came up with, okay? So now you've seen how to solve this manually and electronically. So now we can move to another example. Okay, here we go. Next example, we've got 4 cosine squared theta equals 1 with the same restrictions. We're looking for angles on the interval from 0 to 2 pi that will be solutions to this equation. All right, so the first step again is to isolate the trig function. So here we're going to need to get rid of the coefficient first. Dividing both sides by 4, that's going to give me cosine squared theta equals a fourth. And then I have to get rid of the squared. So we're going to take the square root of both sides. And then that's going to get me down to cosine theta equals. Now remember from your algebra, anytime you take the square root of both sides, you do get a plus or minus answer. And the square root of a fourth is a half. So since we're restricted to one revolution of the unit circle, we're now going to go find all of the angles theta where the ordered pair has an x-coordinate of plus or minus a half. So back to our unit circle, x-coordinate of plus or minus a half. And there will be 4 solutions this time, okay? at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So the solutions are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And again, what we're going to do is we're going to verify that electronically. And this time I don't have the equations input previously, so I'm going to show you how to do this from scratch. So on the left-hand side, we had 4 cosine squared theta. So we're going to say 4 cosine squared x. And if you want to put y equals in front of that, you can. And on the other side, remember it was equal to 1. And so we're going to put y equals 1. And then we're looking for all of the intersections of the two graphs from 0 to 2 pi. And you're going to see that there's 1, 2, 3, 4 points of intersection from 0 to 2 pi. At pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Just like we got manually. All right. Time for another example. Next example, let's look at tangent of theta over 2 plus pi over 3 equal to 1. Now in this case, we have a whole lot of stuff where theta usually is, okay? So what I'm going to do is I'm going to call this angle, let's call this alpha. And so really what I'm concerned with here is in the unit circle, what angles alpha, when I take the tangent of them, produce an outcome of 1. Okay, so remember in the unit circle, the formula for tangent is y over x, and in order for that to be equal to 1, the x and the y have to be identical. So what angles in the unit circle have identical x and y coordinates? Well, that's going to be pi over 4 and 5 pi over 4 have identical x and y coordinates. And so here we can say alpha is pi over 4 or alpha is 5 pi over 4. And then it's at this point that we need to remember that alpha is not really what we're solving for. We're solving for theta. So now we're going to have to go back and substitute for alpha the original angle for tangent. And so that's going to give me theta over 2 plus pi over 3 is pi over 4, or theta over 2 plus pi over 3 equals 5 pi over 4. And then I'm going to need to solve both of these for theta and see if they fall within 0 to 2 pi, because this problem is also restricted to angles of theta between 0 and 2 pi. All right, so here we go. Doing the math, solving for theta. We're going to need to minus pi over 3 from both sides. And so that's going to give me theta over 2 equals, what is pi over 4 minus pi over 3? Well, we're going to pull up our handy-dandy calculator and figure that out. Pi over 4 minus pi over 3, and I think it's going to be pi over 12 negative pi over 12. Negative 1/12 pi is negative pi over 12. And then I'm going to need to multiply both sides by 2. Remember, we're trying to get theta by itself. And if I multiply that by 2, which 2 is understood to be 2 over 1, that's going to be negative pi over 6. Notice that that is not a valid solution because it is not between 0 and 2 pi. Since that answer is negative, it's not within the range of values that my theta is restricted to. So that's not going to produce a solution. So let's try this one. Minus pi over 3 to both sides. And that's going to give me theta over 2 equals, and then we're going to need to calculate that. 5 pi over 4 minus pi over 3. 5 pi over 4 minus pi over 3, that is 11 pi over 12. And then I need to multiply both sides by 2 in order to isolate theta. All right, so that's going to give me theta is 11 pi over 6. Theta is 11 pi over 6 if I reduce that fraction there. So it looks like there should only be one valid solution between 0 and 2 pi for that equation. So what I want to do is I want to verify that with DESMOS. We're doing tangent of theta over 2 plus pi over 3. Y equals tangent of theta over 2, I'm using x for theta, minus pi over 3. And then the other side of the equation was 1. Oh, and that's plus. That was a plus pi over 3. All right, let me fix that. People are probably screaming about that. So plus pi over 3. And then the other equation is 1. Y equals 1. How many intersections from 0 to 2 pi? There is only one intersection for the blue and the black graphs. It is at 11 pi over 6. And so now we have verified what we did manually electronically. And I hope you see the correlation between the arithmetic, the doing it by hand, and the graphing, the abstract and the visual confirmation there. I hope that helps some. All right, let's do another example. Next example, we're going to have sine of theta equals a half. And this time it says solve the equation, give a general formula for all of the solutions, and then list 6 solutions. So now they want the general solution as well as the first 6 solutions, okay? So since we know that the trig function is already isolated, what we're going to do is go to the unit circle and find all of the angles theta that have a y coordinate of a half, y coordinate of a half, that would be at pi over 6 and 5 pi over 6. And these are going to be periodic solutions, okay? So if you think about this, if I go to pi over 6, that's a solution. But then if I make a full circle, I get back to a half, that would be another solution. So when I say periodic, I mean every time I add 2 pi to pi over 6, I'm going to get back to a half, which will be a solution. And that's going to be the same for the 5 pi over 6. If I'm at 5 pi over 6 and I make a full revolution, I get back to that y coordinate, and that's going to produce a solution. So this here is going to be key to writing the general formula, the general solution. So we're going to say theta is pi over 6 plus integer multiples of 2 pi, where k is an integer. Also, solutions are at 5 pi over 6 plus 2 pi increments, integer multiples of 2 pi, where k is an integer, okay? So those are the general solutions. Right here, these are general solutions, and this stuff here on the end, it just says k is any integer. So those are the general solutions. Now let's find the first 6 solutions. Well, obviously pi over 6 and 5 pi over 6 are going to be the first 2 solutions, because those are the first 2 angles we get to if we start at 0. Right? If I start at 0 and I go to pi over 6, that's a solution. And then 5 pi over 6 is the next solution, okay? So then the next solution would be pi over 6 plus 2 pi. That would be the next solution. Pi over 6 plus 2 pi. The next one would be the next angle plus 2 pi. So there's 4 solutions. And then if you think about it, then I'm going to return back to pi over 6 the second time around. If I do another 2 pi, that would be 4 pi, right? I did the 2 pi. Another 2 pi would be 4 pi. And then I've got my 5 pi over 6 plus 4 pi. Those are going to be my 6 solutions that they're going to want here, okay? And all I got to do is simplify those, and I'm going to use the handy dandy calculator to help with that, okay? So we've got, whoops, and it went away. Pi over 6, 5 pi over 6. Maybe we can do this one mentally. That would be 12 plus 1. That would be 13 pi over 6. And this would be 12 and 5 is 17 pi over 6. And then the next 4 pi in 6, 4 times 6, that's 24. Plus 1 is 25 pi over 6. And then the next one's going to be what? 25, 28, 29. Let's see here. 4 times 6 is 24. 24 plus 5 is 29 pi over 6. Man, not the easiest thing in the world. The equation was simple. Sine theta equals a half. But coming up with the general solutions and then the first 6 take a little bit of work. They do. But that's that example done. I think we should do one more example. Let me scroll on down here. And let's do this one in black. Let's say we have cosine of 2 theta equals negative half. Now notice that this is a double angle. I've got 2 theta. And so what we're going to do is we're going to pretend like this is some other angle, say alpha. And we want to find all of the angles in the unit circle that have x coordinates of negative half. Remember, cosine of alpha is x. All of the angles that have a negative half x coordinate. All right, so I'm seeing negative half x coordinates at 2 pi over 3 and 4 pi over 3. 2 pi over 3 and 4 pi over 3. Notice I'm saying alpha because that's taking this angle and reducing it down to a single variable, cosine of alpha. And then what I'm going to have to do is go back and resubstitute for alpha what it's equal to so I can solve in terms of theta. And again, they do want the general solutions first, okay? So that's going to be 2 pi over 3 plus 2 pi k integer multiples of 2 pi and 4 pi over 3 plus 2 pi k integer multiples of 2 pi. Does that make sense? The reason it's 2 pi is because it would take a full circle to get back to those angles. They're periodic solutions, okay? Now these are the solutions based on alpha. I now need to substitute and actually find the solutions based on theta. Okay, so now that's going to look like this. It's going to say 2 theta equals 2 pi over 3 plus 2 pi k, and then 2 theta equals 4 pi over 3 plus 2 pi k, and we're going to just say it's understood that k is an element of the integers, and then I need to solve each one of those for theta. So we're going to divide by 2 all the way through, divide by 2 all the way through, so that we can get our solutions in terms of theta. All right, so now we're going to have theta. Whoops, I don't want to do that in red. Let's do it in green. Theta is, if I do my 2 pi over 3 divided by 2, those 2's will cancel. That's going to be pi over 3 plus, these 2's will cancel, pi k. K is an integer. And the other solution is going to be, if I do 2 pi over 3 divided by 2, that's going to reduce that down to 2 pi over 3 plus pi k. K is an integer. And now I've got my general solutions in terms of theta. And so at this point, I could now go through and find the first 6 solutions for theta. And I think for this one, since it's a little tricky, I am going to go to DESMOS and verify these solutions. All right, so let's start with integer multiples of pi. We're going to start with k is 0. 0 times pi would be 0. That's going to give me pi over 3. For the second solution, 0 times pi is 0. That'll give me 2 pi over 3. And then we're going to do, okay, what happens if k is 1? Then we're going to have 1 times pi, which is pi, which will be pi over 3 plus pi. For the second solution, that's going to be 2 pi over 3 plus pi. And then we're going to say, well, what if k is 2? And you just keep going until you get the amount of solutions they requested. So if k is 2, that first solution is going to be pi over 3 plus 2 pi. And then the other one is going to be 2 pi over 3 plus 2 pi. And then I need to go through and I need to simplify those. So that's going to be pi over 3, 2 pi over 3. That's going to be 4 pi over 3. And this is going to be 5 pi over 3. Whoops, get in a hurry. Slow down. Now then, 6 plus 1, 7 pi over 3. And I'm thinking 6, 7, 8 pi over 3. Those would be the first 6 solutions. And now we're going to verify that with DESMOS. All right, so remember what those are. Now, the original equation, cosine of 2 theta equals -1/2. We're going to say y equals cosine of 2x, x instead of theta, where y equals -1/2. And we want to know if we got the first 6 solutions correct. So the first solution was pi over 3, and then 2 pi over 3, 4 pi over 3, 5 pi over 3, 7 pi over 3, 8 pi over 3. So you can see, using DESMOS to find the solutions electronically, it verifies what we did algebraically, giving us the solutions that we calculated. All right, let's see if we have other examples. It looks like I've got about 3 more examples to get through. So hang tight, trying to give you the best lesson I can here. We're going to have sine theta equals 0.4. And this example, it says use a calculator to solve each equation on the interval from 0 to 2 pi. So now we're back to having theta restricted from 0 to 2 pi. They don't want the general solutions. They just want the first 2 solutions in the unit circle. All right, so to find that first solution, we're actually going to bring the sign to the other side, and that's going to isolate theta. Theta is the inverse sine of 0.4. And then we can pull up our handy dandy calculator and find the first solution. We want to do the inverse sine of 0.4. And let's see, rounded to 2 decimal places would be 0.41. Now there will be another angle, okay? Because in the unit circle, y has a positive outcome in 2 quadrants. There are 2 quadrants where angles have a positive y coordinate. And if we scroll back up to our unit circle, we can see that y values are positive in the first and second quadrant. So what we just found is we just found the angle here. This is the angle we just found, the one in the first quadrant. There will be a corresponding angle that has the same reference angle that'll have the same y coordinate in the second quadrant, okay? So if I know that this angle is 0.41 radians, then I know that this reference angle is also going to be 0.41 radians. And so the actual angle from 0 to here, this is my actual angle, is going to be pi minus 0.41. Does that make sense? If I go all the way around to pi and then subtract that amount, it's going to give me the second quadrant angle. All right, so to finish this off here, our other angle theta is going to be pi minus 0.41. And so that's going to be 0.41. And again, with our handy dandy calculator, pi minus 0.41. 2.73 rounded. And so that's how you use your calculator to find the solutions to the equation. Remember, you can also use DESMOS and check that. Super easy. If I say y equals sine theta, or x, and then I want to know where is that equal to 0.4, we're going to graph y equals 0.4. And you're going to see from 0 to 2 pi that there are two solutions at 0.41 and at 2.73, which are the exact same solutions we just calculated. Okay, so DESMOS again is a great tool to help you verify those solutions. Another example, two more examples. Let's say we have secant of theta equals -4. And again, they want us to solve this equation on the interval from 0 to 2 pi. So again, we have this same restriction. We're looking for angles within the unit circle, one revolution of the unit circle, that satisfy this equation. And so the first thing that I want to do is convert that secant to cosine. That is using a reciprocal identity. The reciprocal of secant is cosine, which means I have to flip the other side. And then I'm going to bring the cosine through to the other side, which will make that inverse cosine of -1/4. And I now have something I can calculate with the calculator. All right, so we're going to go to our handy dandy calculator. And we're going to do the inverse cosine of -1/4. And that's going to give me an angle in radians rounded to 2 decimal places of 1.82. 1.82. Now there is going to be another solution to this problem, okay? And here's how I know that. Because in the unit circle, I know that there's two angles that have an x coordinate that are negative, not angles, they're two quadrants that produce negative x coordinates. And so if we scroll back up to our unit circle, the quadrants that produce negative x coordinates, quadrants 2 and 3. Okay, these two quadrants. What we just found, the answer we just found, is this angle. We found the second quadrant angle, which is going to have a reference angle. Let's call it alpha. And then there will also be another angle in quadrant 3 that's going to have the same reference angle. Okay, so that angle is going to be from 0 around to here. So how are we going to calculate that? Okay, well, look at it this way. Think about this. Starting from 0 to that first angle is theta. What if I started at 0 and went clockwise? This right here would be the same angle but negative. So if I want to know what this green angle is, I need to take my first answer and subtract it from 2 pi. Right? Because if I start at 2 pi and go back a negative theta, then I'll be at the green angle, which is the second angle I need. Okay? So we're going to take the first angle we found and subtract it from 2 pi. And that's going to give us the second answer we need. And pulling up the handy dandy calculator for that, I wish that would stop popping up. We need to do 2 pi minus our first answer, which was 1.82. 4.46 rounded. And those will be the two angles that are solutions to this equation on the interval from 0 to 2 pi. And I do want to check that. So we want to graph secant of theta equals -4 in DESMOS. We're going to check it with, you may be getting tired of seeing DESMOS. I never get tired of it. It's fantastic. All right. So here we have y equals secant of x. And we want to know where y equals -4. Now you may be going to, where did the graph go? Notice that my scale, I can't see -4, so I'm going to scroll up a little bit, and then I see -4 here, okay? So from 0 to 2 pi, do you see that there's two intersections at 1.82 and 4.46? 1.82, 4.46, solutions verified. And this is the last problem we're going to look at. One more example. I did save the best for last. This one is sine squared theta equals 6 cosine of negative theta plus 1. And here it says to solve this equation on the interval from 0 to 2 pi. And there's a couple of things I need to point out here, okay? First of all, the trig functions don't match. I've got sine, I've got cosine. That's an issue we're going to have to deal with. And the second issue is we have a negative theta. We don't really need negative theta, so we're going to have to deal with that also. And so here's the first thing we're going to use to deal with the issues we have. Sine squared theta plus cosine squared theta equals 1. That is one of our Pythagorean identities. And what I'm going to do is I'm going to take the cosine squared theta to the other side so that I can isolate the sine squared theta. And what that's going to do is that's going to give me something that I can substitute for sine squared theta and put the equation in terms of cosine only. So now anytime I see a sine squared theta, I can replace it with 1 minus cosine squared theta. That's part of this identity, okay? So now I'm going to say 1 minus cosine squared theta equals, and then remember the next issue was that negative angle. And so this is where we're going to need to remember our even odd properties for cosine. Cosine of negative theta equals cosine theta. That is also an identity. That's our even odd property for cosine. And so then I can rewrite this as 6 cosine theta, because cosine negative theta is the same as cosine theta. Plus 1. And now I've alleviated the two problems. Now if you notice, everything's in terms of cosine. None of the angles are negative, but it is quadratic. So that means I'm going to have to set it equal to 0. Oh, and I do want my squared term to be positive. So we're bringing him over, and we're bringing the 1 over. And at the same time, we're going to distribute that 6 to get rid of the parentheses. A lot of stuff going on in this step here, okay? All to get the left-hand side 0. So if I bring the negative cosine squared over, that negative will become positive. And then if I distribute the 6, I'm going to have plus 6 cosine theta plus 6, right? If I distribute the 6 to both of those terms. Oh, and don't forget about the plus 1 coming over. That's going to make him a minus 1. And then I need to combine like terms. Okay, so I've got cosine squared theta plus 6 cosine theta plus 5. And now if you notice, this looks a whole lot like a quadratic equation like we would have seen back in college algebra, where cosine theta would be x. So that would be like x squared plus 6. Remember we said cosine theta is x plus 5. And one of the best ways to solve a quadratic, or at least one of the easiest ways, is by factoring. And you should remember how to factor a trinomial. So let's look at how this is going to factor. To factor this trinomial, we're going to have two sets of parentheses. X and x make x squared. The signs are both going to be positive. Numbers that multiply to make 5, that add to make 6, 5 and 1. And then we're going to go back and we're going to substitute for our x's. Remember we said that x really is cosine theta. So at this point we're going to have cosine theta plus 5, cosine theta plus 1. Those are now my factors. And remember, if you're solving a quadratic by factoring, once you get it factored, you need to set each factor equal to 0 and solve. So we're going to say cosine of theta plus 5 equals 0. And we're going to say cosine of theta plus 1 equals 0. And that should produce two solutions here, okay? So for the first one, we're bringing the plus 5 over so that we can isolate the trig function. And let's see. Yeah, this is not good. Let me explain why here. Cosine of theta, if you remember back when we graphed trig functions, cosine starts at the lead coefficient, has a period of 2 pi, and it bounces back and forth between -1 and 1, okay? So those are the range of values that cosine can be. It can only be something between -1 and 1. Well, -5 is not within that range, so this particular factor is not going to produce a solution. So what about the other factor? What if I bring plus 1 over? That's going to make -1. And then I know that cosine of theta equals -1 at pi. Look right back here at this graph. I'm at -1 at pi. And I think I can also verify that from the unit circle, because cosine of theta is x. X coordinate of -1 occurs at pi. So that's going to be the solution to this equation. And I can verify that that is the only valid solution with DESMOS, okay? So strap in. This is the last thing we're going to look at. We're going to put sine squared theta, the left-hand side, in for one equation. Y equals sine squared theta, or x. And then for the other equation, we're going to graph the right-hand side, which is 6 cosine negative theta plus 1 in parentheses. 6 cosine negative theta, or negative x, plus 1. And then if I bring this down and I look at where the green and the purple graphs intersect from 0 to 2 pi, do you see that the only place that the purple and green intersect from 0 to 2 pi is at pi? And so once again, DESMOS to the rescue to verify our manual labor. And that's going to do it for this lesson. Great. All right, so if you have any questions or comments, please post those in the comment section below, or you can text me. And thanks for watching.